right, now that I am the co-host, hello everybody. Welcome to our symposium. Thank you all for being patient and everything. I am Rachel. I am very excited to kick us off on our very last symposium meeting, really anything, round of lightning talks, whatever it is. Today I will be starting you off with our symposium entitled Attempts to Solve the Problem at Hand. This is all of our dynamic relations between the presentations of math problems, individual cognitive factors, and problem-solving strategies. So I'll go first. I'm going to present some work regarding preschool age children's working memory and differences in strategy and explanations in the modality that they use during arithmetic problem solving. Next up will be Fanny, who will present on how variations in visual working memory for adolescents with intellectual disabilities are related to their gesture strategy used during calculation. Then Venera will go next, and she'll be discussing the relations between domain-specific cognitive abilities and how those relate to differences in mathematical stimuli. And last but certainly not least, we have Avery, who's going to go over work regarding how differences in perceptual manipulation of math notation interacts with different cognitive abilities. Lots of cognitive abilities going on today. We're going to try to leave some time for questions in between each talk. We're getting a little bit of a late start, so maybe we'll reserve questions for the end for just a broader discussion. We'll kind of see how it flows. So thank you very much. I will start, just hop in here. All right, so hopefully everybody's seeing my screen and not my notes. Somebody give me a thumbs up. Yeah,
that's all right.
Oh, we love that. Okay, so I'm going to go ahead and get started. So I'm going to tell you about online math adventures. So this is my talk, exploring the relations between children's working memory, math knowledge, and spontaneous gesture use during simple arithmetic problems. And as you can tell, it's all online. So let me tell you a little bit about the background. So I love giving talks to this group because I don't actually have to go too in depth about the math background because usually the author of the studies are present, which is great. So here we know that children's math knowledge and executive function abilities are related to the discovery and use of all of the arithmetic problem solving strategies. So in particular here, we have a nice example. If children were attempting to solve this simple problem, they can use their fingers. They might say a count list out loud as they're trying to work through it. So here we have on the left, 6 and 1, 2, 3, or 3 and 6, 9. The answer is 9. So we have a whole bunch of different things that we can observe as experimenters. You know, we can see their gestures, we can hear their words. There's all kinds of different things that we can kind of look for that can clue us into their overt strategy use. There's different math content, maybe the strategies that they're using and how rapidly they're switching between them, as well as I said before, the modality of the strategy itself. So here I'm going to focus on gesture. So gesture in arithmetic, there is a robust literature behind it. So we know that gestures in particular have been shown to reduce cognitive load, relate to working memory specifically, and they're used more often on harder math problems during difficult parts of problem solving, and usually by younger children. So for the current study, we use a fully online data collection procedure. This was right at the start of the pandemic, so fall 2020. And we were really curious to see if we could kind of take some of the prior literature and investigate some of these same questions in an online format and start to extend it. So use a broader age range to kind of get a look and see what was going on at this time. So here we asked, how do children's age, working memory, and their basic arithmetic scores all relate to each other, as well as how each of those above factors are related to children's use of different strategy modalities. So as we saw in the previous picture, things like gesture, their use of different verbal strategies, so things like verbal counting or maybe decomposition, or even things that aren't necessarily overtly observable, like the use of retrieval if they have something memorized, as well as, their kids, so just simply guessing the answer. And again, since this is this was totally new 2 years ago when we started, how does our data and overall results sort of compare? So our participants were 97 English-speaking children ranging from 5 to 8 years old. We did try to keep these pretty evenly across in different age brackets, so 5, 6, 7, and 8-year-olds, and you'll hear me kind of commonly refer to those age buckets. Our mean age was 7 years old though, and we had a pretty even split across gender. All of our families recruited, signed up, and were consented online using Qualtrics, and we used Facebook, Twitter, Children Helping Science, pretty common nowadays, but I do like to kind of review because back then it was a little bit of a scramble of how do we recruit kids to sign up for our online studies when we were very used to doing them just in lab. So our method consisted of just 3 tasks with an experimenter. So children had a Zoom session set up with one of our trained research assistants, and it took approximately 15 minutes. The Zoom sessions were recorded, and they started with our first game, which is called Math Adventures. So in Math Adventures, experimenters use the screen share function just like this. So their screen would show our Math Adventures game, and they began with an example problem, and they were told that they could answer the problems that we showed them on their screen and use any way that was easiest for them to get to the solution. So the example problem is 2 + 2, and they receive feedback. But regardless of their answers, whether they were correct or incorrect, they would always receive a piece of their treasure map, and they would always find the treasure. So as they went through each of these problems, essentially, it always worked the same. So here you can see what is 4 + 3. The child would solve the problem and give their solution. And we would follow up and ask, how did you get that answer? They may or may not provide an answer to that. And here is their puzzle piece. And so this allowed us to keep the child engaged. And it also made sure that we were accounting for any technical difficulties. If the screen was lagging and we're like, all right, do you see your piece of the treasure map? And they're like, no, I still see the problem. We're like, all right, we'll wait a second. So this was a nice way to kind of stay on top of what's normally, showing them index cards or other in-person format. So here's the full treasure map. After they were all done with the first task, they moved on to the second and third task, which is both a forward and a backward span. So for the forward span, we used color words, and for the backward span, we used animals. The protocol is very similar. So children were read a list of either color or animal words. And the protocol would go up. So you would hear a list of 2 words, 3 words, 4 words. And as soon as the child got 2 words of the same span length wrong, we would enact the end of the protocol here. So their score for both of those measures is the highest span correctly repeated. So for our Math Adventures game, after the video was collected, we would begin by scoring their math score. So just the total correct out of the 11 problems that they received, not including their practice problem. And we also accounted for their strategy modality here. So this would be whether or not their strategy included a gesture, if it was just words alone, so verbal, or something that was unobservable. So again, this could be something that was retrieval or guessing, or something that we were not observing. There was no use of fingers, there was no mouth or lip movements, so no whispering even. And just to move forward here, our intent here was to include things like common coding schemes from Barodi and some of the additional studies like Geary's work with min and max and decomposition, really getting into the nitty-gritty of the arithmetic strategy use. And one of the challenges of the online research is we actually found we had some unaccounted categories here as well. So for example, we had a lot of non-specified coding categories. which, for example, are things like fingers moving in an unidentified pattern, as well as a lot of mouth movements that we aren't able to categorize, as well as some instances of gestures showing total sum, and a lot of off-screen gesture use. Not thankfully totally off-screen, but enough so that we did not want to assign that to a different category. So I'm happy to talk more about this coding going forward. For our working memory score, we have our forward span and our backward span. I'd already talked a little bit about how those were assigned, but we did collapse these into a composite score for one overall working memory composite score. And I'm also happy to talk about that in regards to short-term memory versus working memory and the differences between the tasks. So just as a refresher here for our two questions, we're interested in how all of these factors are related, whether or not each of these are related to what we see and how children are in what they're using in their strategy modality, and how this kind of compares. So overall, descriptively, we did see children use a good amount of gesture strategies at least once, 45% of children. That is the incorrect percentage. 17 out of 97 children used verbal strategy, and 86 out of 97 children used these unobserved strategies. So this is a lot to talk about, right? So what do these consist of? As I said before, these are things like recall, guessing, mental math, and more. Next up, we have each of our correlations. So what is related here? So age and arithmetic, probably not surprisingly, are highly correlated. Working memory, arithmetic, and age are all highly correlated. Consistent with prior literature, age and gesture are negatively correlated, as well as arithmetic and gesture, and working memory and gesture here. So we didn't have any significant correlations with verbal alone, and we can get into that a little bit, but it's honestly because there's not a lot of observations of children simply using verbal alone. Almost all instances of verbal strategies are co-occurring with gesture. And lastly, our unobserved or really uncategorized modality. We have a positive correlation with age, as well as arithmetic and working memory. So next up, we were interested in how this all looks with different strategy modalities. So I'm going to present this with strategy use on the left, or rather on the y-axis, age group on the x-axis, and we'll see it by different working memory level in the different colors here. So first up is gesture. You can see here for our 5-year-olds on the left, we have higher working memory children using more gesture, with the reverse being true for the other age groups, so the 6, 7, and 8-year-olds. Next up, we have our verbal strategy use. There we go. And as you can see, there's just not a lot of this happening. There's not really too much to talk about here, so I will move on. Oops. And here is the bulk of what we are observing, which is unfortunately named unobserved. So these are things where you are not seeing any gesture use or hearing any verbal or observing mouth movements. And so these are, we can compare across to the gesture. So forgive me for it being a little smaller. So the top of our y-axis is the total number of problems. I should have said that at the beginning. So 11 total problems here. So we do see for gesture for our 5-year-olds, for our high working memory group versus for our low working memory group here. We do sort of see the reverse trend for our 5-year-olds, but once you start breaking these into working memory and age, we start drastically reducing our sample size. So let's get into our discussion as I am very much out of time. So how do these all relate? They're all pretty positive, consistent with the prior literature. And there is possible interaction effects between working memory and age, insofar as the strategy that we see children use. But in order to actually investigate these things, we need to continue our online data collection, evaluate additional components such as things like reaction time. We really need to hone in on maybe what's happening for these unobserved strategies. Include additional measures, as well as consider other executive functions such as things like inhibitory control. And that's just a little plug for an additional round of recruitment that we're doing there. So if you have any questions or clarifications, please feel free to contact me. And we are going to jump right into our next talk. So I am going to stop sharing. All right, thank you. All right, Fanny, you are up.
I'm sorry. Good morning and good afternoon. Can you see my screen? No?
Not yet.
Not yet. Okay. I will do it again. So, is it better now?
I don't see it yet, Fanny. Did you do the screen share in Zoom yet?
Yeah, I did the share. So I'm stopped. Okay, I stopped the sharing. I do it again.
Oh, there you go.
Yeah, good. So do you have it full screen?
Not yet. We see your like whole desktop with the PowerPoint on it.
Okay. So
there you go.
Oh, fantastic. Yeah. So good morning or good afternoon, and I'm really happy to present this study entitled Finger Use in Calculation Benefits Depend on Working Memory in Adolescents with Mild Intellectual Disability. Mastering the fundamentals of math is essential for academic achievement and in everyday life. It's crucial for people with intellectual disability to be able to master basic numeracy skills as it leads to a better quality of life. There are questions arising from inclusive school, particularly about finger counting when students grow older in secondary school, for example. And to answer these questions, we need to know if finger counting is a predictor of arithmetic in adolescents with intellectual disability. The present study focuses on finger counting while calculating, further called finger use. To answer teachers' question about accepting, tolerating, or banning finger use in secondary school, we need to know if finger use is a predictor of simple arithmetic in adolescents with intellectual disability. Other factors are known to be related with both finger use and calculation, so we need to know which factors should be included in this study to get a broader view. Mental arithmetic is slower and delayed in students with intellectual disability, and it arises between 10 and 20 years old. It's likely that the learning potential of these students is underestimated. Spontaneous finger use is associated with simple arithmetic in young typically developing children. Finger use was observed in 6 to 10-year-old children with intellectual disability. It was observed in the most efficient groups. However, it was not the focus of the study. Working memory is a predictor of arithmetic too, and visuospatial working memory was shown to relate to simple arithmetic in typically developing students and in students with intellectual disability. There is also a current research question about the relation between working memory and finger use in typically developing children, as it is not clear whether fingers are more used by children with low span to reduce the cognitive load, or by children with high span, as their cognitive abilities offer more flexibility in their strategies choices. We have investigated this question in our paper, but our results will not be presented in this talk today. Finally, dexterity correlates with simple arithmetic in typically developing children. This relation could be mediated by finger-based strategy in preschoolers. Dexterity is 3 to 4 years delayed in children and adolescents with intellectual disability. And dexterity and working memory are associated in 7 to 12-year-old children with intellectual disability. So our research questions are: do adolescents with mild intellectual disability attending inclusive secondary school use their fingers during simple arithmetic tasks? What are the best predictors among finger use, working memory, and dexterity in these students? And are there interactions between finger use, working memory, and dexterity? As studies focusing on non-specific ID are scarcer than studies focusing on syndromic ID, the present study was conducted among adolescents with mild intellectual disability with no known etiology. Students were asked to perform calculation while finger use was observed. They performed the Corsi block backward task and a bead threading task. We first conducted descriptive and correlation analysis. So first, results on the x-axis, calculations are ranked from the most frequently solved to the least frequently solved. And on the y-axis, you can see the successes and failures for each calculation. The black dots represent finger use, and the white dots are the strategies. So we can see that adolescents with mild intellectual disability in secondary school do use their fingers to solve arithmetic calculation. And the more difficult the calculation, the more students use their fingers to calculate. Age is not associated with arithmetic success, nor with working memory. That is consistent with prior studies. And there are no association between finger use and dexterity, nor between these factors and working memory. Working memory and calculation success are strongly correlated. And the relations between calculation and finger use and between calculation and dexterity need further investigation. Then we conduct a model comparison. So we first determined which was the best model. And as several models had very close coefficients, these AICC coefficients, we averaged the best models. So we ran a model selection, and the best model parameters estimates are shown in the table. After a model averaging, the predictors of simple arithmetic appear to be finger use, working memory, and the interaction between finger use and working memory. Interestingly, the coefficient of the interaction is negative. So there is a visualization of this interaction. It shows that the lower the span, the higher the benefit of finger use is. And in the last part of the figure, you can see that it's decreasing, and we can ask, is finger use a drawback for students with the highest working memory spans? Our hypothesis is not this one. Rather than a drawback, finger use could be a strategy used when all other strategies failed for these students. Lastly, we ran a mediation analysis. It is to note that finger use, like the dexterity and working memory tasks, involved finger movements. So mediation analysis between these factors and calculation aim at showing whether these factors have direct effects on calculation. And no mediation effects were found. So here are some takeaways. Adolescents with mild intellectual disability attending secondary school do spontaneously use their fingers to solve simple arithmetic tasks. Finger use, working memory, and the interaction between these two factors predict calculation success in these students. So how to answer the question of finger use in math class raised by teachers? Finger use should be accepted during math class because it supports simple arithmetic success in most of the students. A question arises, however, about the students with the highest working memory spans. We need to determine whether finger use is a strategy they use when all the intern strategies fail, and that would make it a last resort strategy that could be interesting, even if it's failed, but if all the strategy failed, then there is another chance with this strategy, or a drawback, which is not our hypothesis. If it is a last resort strategy, then finger use could be encouraged in math class for all the students with mild intellectual disabilities in secondary school. Thank you. I try to stop my sharing screen.
Well, we probably have time for a question if anybody has a question. And if you want to get set up, we can probably switch that over. But yeah, if anybody has a question for Fanny, you can just hop right on, unmute. No? Okay. Great talk.
Thank you.
Okay, I'm gonna ask the question that everyone asks. Can you see my screen?
You look great.
Perfect. Okay, then welcome to my part of the presentation. It's a little bit different from what Raychel and Fanny were showing us because it's now about adults. It's about expertise and gesturing during proof explanation. And first of all, I want to thank my research team for this collaboration. And as I was saying, it's so we're going to talk a little bit about gestures. So as Golden Meadow said, gestures serve as a research tool, shedding light on speakers' unspoken thoughts. And they reliably predict math thinking. So engaging students in their production might enhance learning. And also gestures perform simulated actions. So they are kind of based on imagery. And also gestures, the experts' proof practices are fundamentally embodied. But it has been said that experts in math might actually be less dependent on gesture production to access implicit knowledge because they have more practice in verbalizing their thoughts. So they are more trained to talk about math, and that's why they might rely less on gestures. And also research has shown that gestures are less frequent in experts than novices. But anyway, experts still do use gestures. And our question was, how do they differ from the gestures that novices use? So we came up with this research design. So our study had two parts. One of them was making sense of proofs. They were symbolic or non-symbolic. And when I'm saying symbolic, I mean in an algebraic way, so with numbers. And when I say non-symbolic, I mean more geometric forms, or if you want visual, so they were represented visually. And then the second part of the study was that experts as well as novices had to explain randomly chosen proofs, and they were either free, so their hands were free, or their hands were restricted. So they had to put their hands on the back. But for the first part of the study, they were looking at proofs and they had to make sense of them. And after each proof, we asked them if they had enough time to follow the proofs, how familiar they were with the proofs, if they understood the proofs, and how engaged they felt. And all this on a 4-point Likert scale. So right now we have more, like the sample is bigger, but everything, like the analysis is still ongoing. So at the moment we are looking at 10 experts and 10 novices. A math expert has been defined as a person that has at least a bachelor's degree in mathematics, and novices are people that have bachelor degrees in other study, or at least a bachelor degree in other subjects that are not related to math. So as you can see here, our experts and novices are on average 21 years old, the experts, and the novices 23.4 years old. When it comes to math anxiety, they're equally math anxious. So almost 20, they score on the AMAS. Then for the numerical IQ, we did the Berlin Intelligence Scale. So in the numerical IQ, they also do not significantly differ. So they have approximately the same IQ. We also asked them for their math grade in high school because that was the last school grade that we could actually compare them, because afterwards when they started studying, they studied different things. So their high school math grade was different. For the experts, it was higher, 5.5 on a 6-point scale in Switzerland. And for the novices, 4.6. So both of these grades are actually sufficient. I mean, good grades. For the math experts, it's actually almost, an excellent grade. Then we also asked them how many hours they spent with math a week. And here they also differ because the experts spend on average 30 hours per week and the novices only 1.6. So for the self-reported measures that we asked them after each proof, if they had enough time and so on and so forth, they did also differ. So they differed on time, understanding, and engagement in both symbolic and non-symbolic proofs, with experts saying they had enough time compared to the novices, experts saying they understood the proof better, and also the experts saying that they were more engaged with the proof. For familiarity, however, we didn't find any significant difference. That means that both experts and novices seem to be familiar with the proofs, and no matter if they are symbolic or non-symbolic. Then for the explanation phase, I was already saying that the analysis is still ongoing. This was videotaped and it will be transcribed and coded for occurrences of gestures and speech during the explanation of the proof. Now, again, just to tell you, these were the two conditions. So either the participants were asked to explain the proofs while they were able to use their hands, or while they had their hands behind their backs. But we will right now just focus on the condition where they had their hands free. And we will also focus on proofs and arguments regarding convergent series. A convergent series is essentially a sum of infinitely many numbers that result in some constant. So here it is 2. So 1 plus 1/2 plus 1/4, which is half of the previous number, and so on. So 1/8, which is again half of the previous number. Those sum up to 2. And usually this proof is shown in a more, or the formal proof is shown in a more algebraic way or symbolic way with numbers, as you can see on the left side of the screen. But it's also possible to show it in a more visual or geometric or non-symbolic way, as you can see on the right side of the screen. So we showed both to all of the participants, and they, in the end, when they were explaining the proofs, they could actually choose whether they are going to refer to the symbolic one or to the non-symbolic one. Oh, sorry. Okay, so now here we have 2 random groups. So you can see 3 images actually on the left side and 3 images on the right side. So these are 2 groups. And if you look at them, do you notice some kind of difference in those 2 groups? And if you are, I mean, I cannot see if you're holding your hands up or something. So if someone wants to say something, you're just allowed to speak up.
A lot of pointing on the right.
Sorry, can you say it again? Can you repeat?
Sorry, I'm unmuted. I see a lot of pointing on the right side. So the 3 pictures on the right.
Yes.
Pointing gesture.
Yeah, so they are pointing towards the screen actually, because in front of them we had a screen, and we were showing them the random proof that they had to explain. What do you think? What is the difference between those 2 groups, or which group might be which group of people, the one that are pointing?
I think you showed the answer. And I saw the answer.
Yeah, I was too slow. You already saw it. Okay, so yeah, so the difference.
I cheated.
Yeah. So the difference is that the ones on the right side are the novices, and the ones on the left side are the experts. And you're right, the novices were pointing a lot towards the screen. So now, just to show you, we will focus now a little bit on the experts. So here, this expert is discussing a proof by actually referring to the more geometric visualization, let's say. And she she kind of does this movement, like chopping movement, and she's talking about areas. So the whole area is this length would be, and then she goes down, does this chopping, one slice, and then the next slice. And so she's showing how this adds up. So these slices are adding up, if you can remember the proof from before, how these add up to an area. Then the next expert here, he's holding out his left hand and indicating, indicating the first term, and then does this movement by showing with the second hand and points to the first hand, saying that it becomes the same as the first one. So somehow referring from one, like from the first term, the second term adding to the first term, becoming the same. And says this also while doing it. And here's a third expert. She's pointing to her left hand with her right, designating X, so showing X, and then Y takes its place on the right. On the right of X in the space in front of her, then Z to the right of that again. So she's doing the movement. I don't know if I'm showing it the right direction. I guess so. So this was the most common gesture that we were seeing. And it was shown a little bit, of course, with variation, but at least once by every expert and in half of the novices. So we saw them, so to say, twice in the experts compared to the novices. Oh, yes. So here you can see the movement actually with the arrows. I'm sorry for that. Okay, so, and here we see a novice, and you can see that he's pointing at the screen. So he's referring to an element on the screen, and then he rotates his wrist to refer to the previous element. And he's also, when he's talking about it, he says, so that term. And this is also different compared to the experts, which were talking about this. So it's different, it's that compared to this, and the pointing is towards the screen instead of in a peripheral area. So this behavior actually happened also in experts and also in novices, but novices were doing it more frequently than the experts. So to sum up, we've seen that experts were talking about proofs as if they would be closer to them or in their periphery, where they can grasp the terms and talk about them in a more, like in a closer way, because they were also referring to this term, compared to novices, which were pointing towards the screen as if the terms, like as if math would be further away from them, and as if they couldn't grasp math in that way as expert might. But as I said, we still are analyzing the data, and we still have many experts and novices to compare. And also, this is actually part of a bigger project, and we also did some EEG. So if any one of you knows about EEG and could help us with thinking about how we can relate maybe abstract and concreteness in experts and novices while using EEG, then you're welcome to let me know. So thank you for your attention.
That's awesome. So if anybody has a question for Venera, just while Avery gets set up, Avery is next. So yeah, does anybody have just one question? Oh, okay, we have 3 questions. The first question I saw was probably was the first hand over here. All right, I see Hans Christoph hand. So why don't you go first? And then we'll save the rest for afterwards.
Hi, I have actually two questions. Maybe you answer one if you're there. First, the first question is, which of these gestures, how specific is that to mass? I mean, some gestures might be very specific, like the addition gesture you showed. Others, like whatever showing magnitudes, might be less specific. And you could, whatever, you could also have it in other speakers, which are experts in something in general. So is it experts novice distinction that you're making, or is it mass versus non-mass experts, domain specific and domain general? And the second question, what was not fully clear to me, maybe I missed it, was how well did the novices understand the proofs? Because what you wrote, it's like, so it's some of this gestures rather where they pointed to something, pointing gesture, rather seem to me they are describing what they see rather than explaining what they understood. So I wonder if it's, different cognitive processes, whether describing something which I maybe do not fully understand versus explaining something which I have understood and therefore go on a totally different level. So these are two questions: domain specificity and explanation versus description.
Okay, so for the first question, I don't know if I can really answer that because we only asked them to explain math proofs. So I don't know if we had a condition where they should explain something else, like a story or something, then maybe we could see if the gestures would differ. If, let's say, the math experts would use same gestures in both story and math, or if these are really specific to math. I think because some of the gestures were actually happening also for novices, novices were also using them, or experts were also using them, I would think more that it has something to do with math. And you're right about the novices, when they just point to the screen, you could think that maybe they are just trying to explain what they saw, but they don't really understand it. For the second question, they did actually understand it, the self-report. I mean, they were saying that they understood it on a scale from 1 to 4. They had a mean of 3 point something, like 3.2 or something like that, which is high enough to understand it, but we also will have to code for how well they actually explained the proof. So that is also still ongoing, but that's a very good input. Thank you.
And we can loop back to other questions. I know, David, you had your hand up too, but I want to jump to Avery. And Avery did have a note here that her internet is lagging just a little bit, so be patient if her slide advances before her voice or vice versa. But take it away, Avery.
Thanks, Rachel. And I will double check. Can you all see my screen okay?
Yep.
Well, I'm really excited to share a study that Jenny Chan, Aaron Ottmar, and I have been working on this past year, looking at the relation between inhibition skills and perceptual cues and arithmetic performance. And if you're interested, you can see our pre-registration on OSF too. So students' problem-solving accuracy and efficiency are math ed, but they may be impacted by the way that math problems are presented. And this is because our reasoning and performance in arithmetic are influenced by our perceptual processes. So the ways that we perceive incoming information changes the way that we interpret it and actually act on it. So visual features of problems, like maybe the arrangement of symbols and color, can be used as perceptual cues to direct students' attention towards important information. And the perceptual cue that we're really interested in is the physical spacing between symbols and operands. So on the left is an example of spacing that's congruent with the order of operations. The 3 times 4 are closest together, which creates this little objects that actually incline students to perform that calculation first. In the middle, you'll see neutral spacing. And on the right is an example of incongruent spacing, where the 5 plus 3 and 4 plus 6 are closer to each other, which creates two groups of objects that, if calculated, would be incongruent to the order of operations. And research has shown that when congruent with the order of operations, students are more accurate than their peers. But when students see spacing and expressions that's incongruent to the order of operations, they're more likely to make mistakes and take longer to solve problems, so reducing accuracy and efficiency. And this is true for children and adults, even college engineering students, suggesting that perceptual are really difficult to ignore. But little work has considered how this effective spacing might be impacted by students' individual differences. So we predicted that students' inhibitory control may play a role in this. Intuitively, students may use inhibitory control in math when they suppress the urge to use less efficient in exchange for more efficient ones. For example, suppressing the urge to count all numbers when they're adding two values, as opposed to starting from the larger number. Students may also use inhibitory control to ignore distractions while they're problem solving, such as ignoring loud noises in a busy classroom or ignoring irrelevant information like perceptual. But what's really interesting is that while the relation between inhibitory control and math performance seems intuitive, the research has shown conflicting results. And this might be because different studies have used different tasks and looked at different facets of math performance. So it might be that the relation is dependent on the task used to measure inhibitory control and that connection to interest. Either way, more work is needed to understand whether and how this relation exists. So in this study, we aim to replicate prior research on the spacing effect and extend this work by investigating the role of students' inhibitory control. First, we asked, how does students' performance on order of operation problems, as in both their accuracy and response time, vary between problems with congruent and incongruent spacing? And we predicted that students would be more accurate on and quicker to solve congruent problems than incongruent problems. Second, we asked, how does students' problem-solving performance vary by their inhibitory control? And we predicted that students with higher inhibitory control high performing on all of the order of operations problems. And finally, we asked, is there an interaction between students' inhibitory control and performance on order of operation problems? And since this is a newer contribution that we're making with the study, we didn't actually have a prediction for this question. So we recruited participants in undergraduate psychology pool at our university. We ended up with 174 students in our analytic sample. These students were roughly half female identifying. They were averaged about 19 or 20 years old, and they spanned from a student in high school enrolled in college classes to a couple fifth-year students at WPI. So these students studied by clicking on a link in their browsers to the 30-minute online study. We used a within subjects design, so all students followed the same procedure. First, they completed a version of the animal Stroop task, where they were asked to click on the image of the animal that's larger in real life, not just the animal that's larger on screen. So students completed 4 practice trials, 64 test trials. Next, we wanted to measure students' baseline performance on order of operation problems. So they completed 16 neutral problems like the one shown here. And then after that, they completed 32 experimental problems. Half of these problems had congruent spacing, half had incongruent spacing, and they were all presented in a randomized way. To measure students' performance on these tasks, we used calculations that had already been used in related work. Students' inhibitory control was calculated as the difference between their median response time on congruent problems and incongruent problems for the problems that they answered correctly. Then for all of the order of operations problems, we calculated students and their median response time on correctly answered problems. So here are the descriptives for our focal variables. Importantly, you can see that students were high performing on the inhibitory control task, and they were comparably accurate across all 3 problem types. So to answer our research questions, we conducted a was to analyze students' accuracy and response time separately. For research question 1, we treated students' baseline performance as a continuous independent variable. And for questions 2 and 3, we added inhibitory control as a continuous independent variable to the models. So first, you can see on the left that there were no difference in accuracy on congruent versus incongruent problems when we control for their baseline performance. However, you can see in the graph on the right that students actually took significantly longer to respond to congruent problems than incongruent problems. And spoiler alert, that was the most interesting result. There were no effects of inhibitory control on students' response time, and incidentally, there were also no interaction effects. So putting these results together, the findings were opposite of our predictions. First, a lot of prior work has shown that students are more accurate on congruent and neutral problems and worse on incongruent ones, but we found comparable accuracy across all the problems. So we think that our study sample and stimuli may have limited the variance in students' performance. The order of operations problems may have been too simple for college students, especially from a STEM and engineering school. So looking ahead, we plan to conduct the study with algebra students to see whether these findings replicate with a sample that would be more appropriately matched to the content that we use. And then second, students were slower to answer congruent problems than incongruent problems. And we think this may have been a result of our study design. So students completed the animal Stroop task before they did the order of operations problems, which may have inadvertently primed them to think about using inhibitory control while they were going through those problems. And presenting problems in a randomized order might have impacted their performance too. Most work has blocked problems by problem type. So we're one of the few that have actually tried this randomized order. So if students were using inhibitory control and relying on perceptual cues, but they were switching back and forth between problem types, they may have taken longer on congruent problems than congruent ones. And this possibility aligns with the negative priming paradigm, which posits that if an individual views a stimulus that should be ignored, followed by a stimulus that should not be ignored, their accuracy and response time actually suffer on the latter task. So we think that these findings mean that our next step in future work should look at performance to see if switching between problem types is more difficult and when that's the case. And finally, students' inhibitory control was not related to their performance, but these results add to the conversation on whether and how inhibitory control may be related to math performance, just by looking into it with college students and in relation to. And since inhibitory control typically increases with cognitive development, we plan to replicate this study with a younger sample where there's likely to be more variance in students' inhibitory control. So taking all this together, we've extended prior work on the spacing effect and work on the relation between inhibitory control and math performance. Students may be differentially impacted by viewing perceptual cues in math problems. And ultimately, we really hope that this work leads to recommendations for teachers and content developers to consider when they design online instructional activities for math. All right, thank you all so much.
Does anybody have any questions for Avery? I see lots of clapping, but
There's a question in the chat, I think, or a comment.
I'm reading Renee's comment now. I have not looked at the new suite of tools, but that is so interesting to think about how these tools for adding perceptual cues may already be available in ways that we haven't thought of, in ways that we could even use in our own work and presenting. So I'm happy to hear that you've also thought about this question.
Yeah, especially because, I mean, some of these tools are brand new and just released as in like weeks or months ago. And I went to a session from the Learning Disabilities Association, and somebody from Microsoft was there who has dyslexia and also advocates for dyslexia in the United States in the Boston area. And so she zoomed in with our class, and I was just really sort of blown away about the small things. So these are like small interventions that don't require, it's not like, it requires like a 6-week study or something like that to, for an actual intervention to like rebuild neural networks or something. It's like, these are things that teachers can take and implement immediately in the classroom if we know that these are actually things that can impact. So like we have to have that evidence that yes, this, other than just anecdotal, but yeah, I've really been thinking about that a lot, just across that whole executive function, which is like pretty much anybody with a disability of any sort has some, there's something going on with executive function there. So take a look, because on Microsoft Suite, look under the like neurodiversity, or I forget how they label it, but take a look at those. They're pretty amazing.
I will definitely take a look. Thank you so much for sharing that. And if you would want to talk with our team more afterwards, feel free to follow up with us.
And I know we are a little bit after the 10 o'clock cutoff, but I figure we can keep going with a couple of questions before we end here. I know, David, you had a question earlier for Venera, if you wanted to ask your question.
Yeah, thank you. Venera, thank you. It was a really interesting talk. And my question was whether you saw any association between the type of gestures used and the accuracy of participants' performance, independent of whether they were experts or novices.
I don't actually know about the accuracy. My colleague is here. I don't know if he knows something. Okay, the answer was no. So we still didn't.
Okay, thank you.
Didn't analyze that.
All right, if there's any other questions, anybody else? No? All right, everybody. Well, thank you so much for coming to our Monday morning, afternoon, depending where you are in the world, symposium, and the last one for technically 2021, 2022, right in time for everybody to go to Belgium. So thank you all for attending, and have a wonderful rest of your day.
Thank you.